Hello, in this video let's discuss third question of today's contest. You are given integer n and undirected graph with 10 nodes from 0 to n minus 1. This is represented by 2D array edges, indicates a node, indicates an edge between ui and vi with that can be removed at time I. You are also given an integer k. Initially graph may be connected or disconnected. Find the minimum time such that after removing all the edges with time less than or equal to t, the graph contains at least k components. Return the minimum time t. The constraints are n is up to 1 if I and time is up to 1 in n. So let's take a simple example and let's think how can we do this. So this is the original graph. Let's assume this is the original graph, and we can remove at a point of time we can remove all the edges with a weight less than or equal to that time. So let's assume that this is the expiry time of 4 of this edge. So after time 4 this will be expired, and similarly all other edges. So in this way we have to find the least time such that the graph will have at least k components. So let's start removing from smallest edge and observe some things. So this is the original one. This is the original one. So I have removed the one first because it will be the one that will be first expired. So these both are one. So let's remove these both. After removing this will be the new graph. These both edges will be expired. And let's remove 2 because this is the next least one. After removing 2, after removing 3, after removing 4, and after removing 7. So after all the edges, the graph will have exactly 8 connected components because each node will be individual component. So in this way, if we try to observe the number of components, initially it is 3 because this is the first one, this is the second one, and this is the third one. And similarly for this one, there are 4 components, and similarly 5, 6, 7. So if we observe one thing, as we are removing more edges, as the time is increasing, we are removing more edges, and therefore the number of components is going to increase. So let's assume this is the graph where the components increase. So there may be a case where there can be a constant in the components and then increase, but indirectly it is just like increasing value but not decreasing at any point of time. So this is the original graph. Let's assume this is the graph representing the number of components as we remove the edges. So initially component is 1, and let's assume this is the 5, this is 10, and so on. And now the question asks us to find the minimum time to get at least 12 components. So let's assume this is the point 12. So as this is already increasing, instead of brute forcing every time, for example, what is the first idea? We can start from 1. So we will try to remove all vertices and then we count the components. If this is greater than or equal to k, then return this. If that is not, then we will remove all the edges with weight 2 and we will count again, and similarly for all edges. But this is wrong because it will give TLE as we are doing BFS for every time and the time is up to 1 in n. So in this way it will give TLE. So this is not the original. This is not the correct one. So if we try to observe now, the components are increasing. So instead of removing every time, we can start with the value of mid, and at that mid we can find the number of components. If the components is so based on the count at the components of mid value, then we can find whether we can go to next component or not, next weight or not. So simply bind search, because the array is monotonic, we can find whether at which index we want the number of components to be more than k. So for a mid value, find the components count. If it is greater than or equal to k, it means that we already found an answer. So save this as a possible answer, and we want to get the least value, least time to get the answer. So try to reduce low. So because for mid plus 1, mid plus 2 all, the answer will be greater than or equal to k. But we want the least time possible. So simply answer is equal to low. We are storing the answer, and high is equal to mid minus 1. So we are trying to reduce the search space to mid minus 1 because we want the least time, as already we got an answer. And similarly, if it is greater than k, so it means that this is not our answer because we want, sorry, if it is less than k, then we want greater than or equal to k, so this is not the answer. So if this is not the answer, then any value which is less than the mid value also cannot be answered, because we discussed that this is surely increasing, greater than or equal to increasing. So only we can try higher values. So simply we can increase low is equal to mid plus 1, so that we are searching a new space with higher value of mid. So low is equal to mid plus 1. So how can you find components for everything? So low is equal to 0 initially and high is equal to 1 in n plus 1. Because the time is 1 in n, the maximum time can be plus 1, which can be just safer upper limit. So how many times we will run the binary search loop? It is at most 31 times, because we will reduce every time high by 2. So in this way we can find it can run at most 31 times. So for every mid value, if we make a graph with edges greater than mid, because we assumed that for a mid value x, we will remove all the edges with weight less than or equal to x, so that they are expired. So if we only use edges with greater than mid, it is indirectly removing less than or equal to mid edges, and then we can find the number of components by BFS or DFS. But we can do this But let's discuss a better approach, which can be solved by DSU. We are solving this by DSU because of mainly two reasons. Because I have recently started DSU playlists, so this can be a better add to that. That's why I'm doing this one instead of just BFS or DFS. And the second one is BFS or DFS may give it yearly, because comparatively with respect to BFS or DFS, the DSU will have less time complexity in merging the nodes and finding the answer. So let's discuss DSU. Why is that used? So DSU is mainly used for two situations. The first one is we have to find whether two nodes are connected or not in OF1. So let's say we have two nodes and we have to find whether they are connected or not in OF1. We can do this by BFS or DFS in OF1, but we don't do that. We want in OF1. We can use DSU in that case. And similarly, if there is a big graph and we just want the number of nodes that are reachable by a given node, then we can simply do by BFS again in OF n, but we want in OF1. Even then we can use DSU. So these two are the main conditions where we can use DSU. But in this case we can use both. But I am discussing DSU because BFS can give daily. So what is the main idea by DSU? So DSU is the main idea where every component is represented by unique leader of that component. So for example, this is the given graph. After traversing all, the unique component of this one is 1, this one is 3, and this is single, so it is itself, and this is itself. So in this way, DSU helps to find the unique component, unique value for every component. So for every value in that component, the unique value is same. So we can simply traverse the whole values and we can insert the unique component in the set, and then we can find the number of different components. So the time complexity of DFS is of m plus n because it is a standard m plus n, and for DSU it is simply of n plus some of constant, because the functions used by DSU where merge and find are O of n approximately, and they are far less than O of n. So O of n this n is due to traversing all the nodes and inserting into set. So DSU is surely faster than BFS. Let's check the code. So initially we are inputting the values and calling the minimum time. So low is equal to 0, high is equal to 199 plus 1, and mid and answer. So we are using binary search to find the mid value. So for this mid value, we are finding whether the components are greater than or equal to k. If that is the case, then answer is equal to mid, and we are reducing the higher space because we already got the answer. Else reduce the low, because for any value which is less than mid, it is not possible to get greater than or equal to k because we did not achieve here. And what is check doing? It is simply initializing parent and size, and we are initializing every parent of node to itself. Every node will point the parent of it to itself. While merging, we will change the parent and sizes. So hope you have checked any standard playlist of DSU to get an idea. And we will merge these both, and then we will traverse all the nodes, and if that is parent is equal to itself, so we can use a set to store, or the ultimate parent node of ultimate parent is itself. So if parent of I is equal to I, it means that we are already the ultimate node. Then increase the components and finally return whether components is greater than or equal to k. So if that is the case, let it return true. If you have any doubts, comment below. See you in the next video.